Hi, I'm Alistair, and this is an electronic puzzle safe I made. To open it, players must use this rotary input to enter a code, which is displayed on this 7-segment display. But it wouldn't be much of a puzzle if players simply knew the code they had to enter. So instead, they're going to have to be SafeCrackers. Now, when a digit is set to the correct value, there's a sound effect played, the electronic equivalent of a tumbler falling in a lock. It's quite subtle, so if you were to use this in an escape room, perhaps players might find a stethoscope and they'd have to hold it up against the safe to hear it. I'm just going to stand as close as I can and hopefully you'll be able to pick it up on the video through my microphone. And then to set the next digit, what you need to do is rotate the dial in the opposite direction until you hear that one has been set. And you alternate clockwise and counter-clockwise to proceed through the whole code. So even though it's purely electronic, the input and feedback are meant to somewhat emulate the mechanics you'd associate with cracking a traditional safe, which I'm now going to try to do. So I can't actually see the display here. I'm just going by the audio feedback as I rotate this dial, but hopefully, if I get this right, it's quite stressful doing this on camera, you'll be able to see the code appearing. If I get it right. When the correct code has been entered, the LED pattern changes and a lock releases that enables the safe door to be opened. Now, the safe itself is actually one of those small keypad safes you often find in hotel bedrooms or something like that. I bought this one on Amazon for just under £20. In the rest of this video, I'm going to show you how I modified it to create this puzzle. So let me start by showing you this in normal operation. So you've got your keypad over here, and if you enter the correct pin number, that will unlock the safe. Now it doesn't actually open the door immediately. You've then got to twist this dial and that enables you to open the door. So it's actually a mechanical lock. These are the bolts here which slide across, and those are what are locking the door in place. What the keypad does is simply prevents you from turning this, and I'll show you the mechanism that works that in a moment. Now if you lose the pin code for any reason, there's a little access panel here, and if you put a key into that and twist it round, that will also let you rotate the dial that moves the bolts across. So that's the normal way of using this safe. Now let's take a look at the internals. So you'll see that there is a screw on the side here, and if I take this cover off the battery panel, there is also a screw underneath there. Now if I remove both of those, then we should be able to take this, just slide this off the back, hopefully. Give it a bit of a wiggle. The keypad on the front is wired to the electronics on the back, so I'm being a little bit careful. There we go, just not to break that. So you'll see that there's a membrane there that is connecting the PCB here to the keypad on the front. This is the lock mechanism that I was talking about, so it's quite clever really. This are the locking bolts that come across, and the dial rotates them like that. When it is locked, this solenoid here pops up that prevents the bolts from being pushed back again. And the effect of either turning the key in the front or typing the correct keypad pin code causes this solenoid here to be depressed down, and that enables the bolts to be retracted again in and out. Now let's take a closer look at the PCB. So to do that, I can unscrew this little screw here, and hopefully then I'll just be able to lift that off. And now I'm just going to rearrange these components so you can get a better look at them. So all I've done here is I've unscrewed and removed the interesting parts from the rest of the safe, leaving essentially an empty shell behind, just so you can get a better look at how these work. So here we've got the front panel with the keypad. Here we've got the PCB that's controlling the logic. It's got a small microchip there, a buzzer, some LEDs and a handful of other components. And here we've got the solenoid, which is what locks the ability to rotate the dial here. Now if I just show you again the process for unlocking it. So I enter the pin code on the keypad here, you can see the LEDs light up, and then when I enter the last digit, if you watch the solenoid here, you'll see it retracts for about 3 seconds. And it's in this period you could have rotated the dial that would have moved the bolts across, enabling the door to open. But what I'm most interested in doing is working out how we can modify the components I've got here. So perhaps instead of having a numeric keypad input, I could have a different input into the chip here. Or perhaps we could just trigger the solenoid directly. It's just got 2 power wires going to it. I don't think I'm going to be able to reprogram the logic on the chip itself here, but maybe I could replace the PCB with an Arduino or an ESP or something like that instead, but retain the same input and outputs. So I tried out a couple of different ideas and this is what I ended up with. So I've removed the keypad from the front door of the safe and instead replaced it with this blank plate which I 3D printed, and that's just got space for these 3 LEDs. Now I'm using PL9823 programmable LEDs. These are a little bit like NeoPixel's WS2812Bs, but instead of coming on a strip, they are individual 5mm LEDs. So you can use them in place of a regular LED, but you can change their colours, you can set them to have lighting patterns, chase sequences, etc. So I'm using these to indicate the status of the safe. Now I've put the solenoid lock back where it was originally, but instead of wiring it to the control board that was here, I've taken the wiring for the LEDs and the solenoid out the back of the safe through this cable here and into a new sort of control box that I've added on the top. Now, if you wanted to use this in an escape room, what you could do is you could mount all the additional components here actually within the safe itself. This is surprisingly solid. The safe is actually made of steel. It's quite heavy, but for just ease of development and to be able to show it to you, I've just put these in a laser cut plywood box, which I've put on the top. And if I just take the lid off, I can show you what the components in there are. So we've got the wires coming in from the safe here. They are going to an ESP32 microcontroller. And that has also got the rotary encoder knob on the front here, as well as the 8-digit 7-segment display. That's being powered by a MAX 7219 chip. Here I've got a small piezo speaker, and that's what's going to be used to give the audio feedback when one of the digits has been set to the correct value. And finally, I've got a relay module, and that's what the ESP32 is going to switch over to provide power to the solenoid lock that's going to open the door on the front. And here's a diagram to illustrate the wiring between those components more clearly. So I've got my ESP32 in the centre here. I'm not actually using any ESP32 specific functionality in this project. You could use an Arduino Uno or Nano board here instead. And in fact, in some ways, that would actually make it a little bit easier, as I'll explain in a moment. But I tend to use ESP32 as my default microcontroller in all new project builds at the moment. It's a modern controller, it's just as cheap as an Arduino, and it's got significantly more features. It's faster, it's got more memory, it's got Wi-Fi and Bluetooth on board, etc. So that's what I'm using as the base controller in this project. And then I've got the various components wired around the outside. So I've got the rotary encoder here, that's connected to ground to VCC, and it has a clock and a data line connected to 2 GPIO pins. The 8-digit display up here has 3 GPIO pins, which are connected to its data, clock and chip select lines. The PL9823 LEDs, they use just a single GPIO pin, which is connected to the data in leg of the first LED. You can then daisy chain as many LEDs as you want, wiring the data out leg of one to the data in of the next. and they also need VCC and ground. And here I've got a relay module which is used to supply power from this DC supply to the solenoid on the front of the safe door. Now the safe is originally supplied with 4 1.5 volt AA batteries, which means it has a nominal power supply of 6 volts. And that's why I've written 6 volt DC here. Now in practice, an AA battery typically has slightly under 1.5 volts. So the solenoid appears to operate completely fine from only a 5 volt supply. But I thought I'd point out that it is a nominal 6 volts because if the voltage applied is too weak, the latch won't open and you won't be able to open the safe. Now, on the subject of voltage, let me return to my previous comment about Arduinos. So, Arduino boards operate at 5 volt logic. What that means is that if you write a high signal to a GPIO pin on an Arduino, it will get set to 5 volts. Now, I'm using an ESP32 which operates at 3.3 volt logic. So writing a high signal to any of these pins only sets them to 3.3 volts. Now, does that matter? Well, the question is that the modules which I'm attaching here, the programmable LEDs, the 7-segment display and the relay module, are originally designed to work with 5 volt logic devices. Now, there is a degree of tolerance though in the voltages that they accept. So the wiring that I've shown here is exactly the wiring which I actually used in the demonstration video, and that appears to work absolutely fine. I am using 3.3 volt logical output, and I'm also supplying them with only 3.3 volt logic on the VCC pins. Now, technically, that is slightly operating out of their spec though. They typically need a value of higher than 3.6 volts or possibly 3.9 volts to register as a logical high on any of these pins, and I'm slightly underneath that. So if I was doing this strictly correctly, what I should introduce here is a logic level converter on all of these signal lines here that are going to the 5 volt devices, and also be supplying them with 5 volts, which you can get from the VE pin here, on the VCC lines. Now, if you're using an Arduino, you don't need to worry about that because that already operates at 5 volts. So you can supply VCC at 5 volts and the signal lines here will operate at 5 volts. Or you can do what I'm doing, which is to use an ESP32, supply 3.3 on the VCC and also 3.3 on here, but know that if you do that, you are technically slightly outside of the technical specifications. It appears to work absolutely fine in my case, but I'm warning you about that. Or alternatively, if you do want to use a 3.3 volt device like an ESP32, but do it the correct way, what you should do is to use a logic level converter on any of the data lines and then also supply 5 volts on the VCC line. And then the final component I've got over here is the piezo, which I'm using as the audio output. And you'll see I've put a resistor in line here from the GPIO pin that is going to drive it. And this resistor is there for a couple of different reasons. The first is that we want to protect the GPIO pin on the ESP32. Now, we're using a piezo transducer as an output here to convert an electrical waveform sent from the ESP32 into a noise, a sound. But it also works the other way. If someone were to hit the piezo membrane, the vibration will generate an AC waveform, and that could feed back and damage the ESP32. So we put a resistor in front of the GPIO pin just to block some of that incoming possible current spike. And we also want to protect the piezo itself. If you buy one of these components from a reputable electronics supplier, it will have a maximum current that can be applied, so that when we drive it from the output pin of the ESP32, we add an inline resistor to keep it under that value, much in the same way as if you were to add a current limiting resistor when you wanted to light up an LED. You place that in series in the circuit between the GPIO pin that you're driving high and ground. Now, unfortunately, this was a piezo that I just found lying around, so I don't have a data sheet and I don't know its parameters. So I did a little bit of guesswork from looking at some similar parts online. Now, the maximum drive current from an ESP32 GPIO pin is about 20 milliamps, and as mentioned, that's at 3.3 volts. We know from Ohm's law that R is V over I, resistance is voltage divided by current, so that would translate to 3.3 divided by 0.02, which is a total of about 165 ohms resistance in this circuit. The piezo already has some internal resistance, so I've added 150 ohm resistor in front of it, which when added to the internal resistance, that will keep within the 165 ohm limit. The final reason, of course, is that we actually want to limit the volume of the clicks and the beeps and the boops that are coming out of the piezo. For this puzzle, we actually intentionally want the sound output to be pretty quiet, and the greater the value of the resistor placed here, the more the current is going to be limited flowing through it, and the sound will get quieter and quieter. So you might need to play with this value a little bit, but I recommend starting with a value somewhere between about 150 and 200 ohms and working from there. And here is the code listing that is running on the ESP32. This is a relatively long code compared to some of my projects, but to be honest, it is only reusing components that I have already used in previous projects. So if you followed along with any of my other tutorials, hopefully a lot of this will look familiar to you, and I'll just sort of go over some refreshers of what's going on. So I'm making use of two external libraries. I'm using the LED control library to help interface with the 7-segment 8-digit display. That uses a MAX 7219 chip. And I'm also using the excellent fast LED library for controlling the PL9823 programmable LEDs. This is the same library I always use every time I use WS2812B strips or anything like that. And then we've got a section of constants, which is where we define essentially configuration settings for the control. So I define the pins that the LEDs are connected to, that the encoder is connected to, that the relay is connected to, and that the piezo that creates the tick sound is connected to. These all reflect the wiring diagram I just illustrated, but obviously if you change that, you can just update these values. And then we say the total number of programmable LEDs that we're going to have in the strip on the safe door. This is the number of milliseconds, which if that elapses after the safe has been unlocked, it will cause it to automatically relock itself again if that number of milliseconds elapse. And then we actually have the solution code that players are looking to enter. It's going to be 8 characters long, and I've just set that to 1, 2, 3, 4, 5, 6, 7, 8. Now, in the version of the puzzle which I've actually demonstrated, players never see the code at all. They are doing this as an audio puzzle. So you could set this to just 1, 1, 1, 1, 1 if you wanted to, it doesn't matter. All that will happen is that when a digit has been set to the correct value in that position, there will be a different sound that players will hear, and that will let them know they've got it correct. You don't actually need to have the display at all. You can do it entirely orderly, but I think it's a good idea to have the display as not only as an aid for any players who might be orally impaired and not be able to hear the sounds or something like that, just as a secondary way of solving the puzzle as well. So if players are finding it too hard to notice the sound effect when the code is set correctly, you can have them look at the visual display of the code instead. And we go on to some globals. This is where we initialize any global instances that are going to be shared throughout the rest of the code. This is the LED control object that we're going to use to set the 7-segment display. And this is the array of LEDs that we're going to have on the front of the safe door. For entering the code, as I sort of tried to demonstrate in the video, what happens is you rotate the dial in one direction, and for as long as you continue rotating it in the same direction, what will happen is it will increment the digit that you're currently setting. If you change direction and start rotating it in the other direction, what will happen is you will begin setting the next digit in the code, and then you continue turning in that direction to increment that one instead. So we need to keep track of what the last direction input into the rotary encoder was. So this value here will either be 1 for clockwise or -1 for anti-clockwise, and then each time the rotary encoder changes, we'll compare it to the previous value to see whether it has changed direction or not. This is the current digit in the code that the player is setting. So this is the 0th digit right the way up to the 7th digit here. And this is the value that has currently been set. So this is the value that is being displayed on the LED control at the moment. In both cases, for the input code here and also the solution code up here, because these are character arrays that I'm setting, notice that I'm defining the array to have one more element than you'd think necessary. The code length is 8 because it's got 8 characters in it, but the array length has to be 8 plus 1 because character strings need to be terminated with a trailing forward or backward stroke 0 rather at the end, which is sort of a null terminating character. This is just a if you're not too familiar with C code, that might seem a bit weird, but that's basically to let it know that it's reached the end of the character string. There's a special character that gets inserted that looks like that, and you need to leave room in the memory that you've reserved to hold this character array for that additional character. So that's why I've got the +1s here in both the input code and the solution code that we'll compare it to. I've defined an enum of just the different states that the safe can be in. It can really only be in 2 states. It can either be locked or unlocked. So I could have done this using a Boolean flag instead that just says is locked, or I could have done it with an integer value of 1 or 0. But the advantage of enumerations is that it's much easier to see referred to in code. You can actually have a word saying if state equals locked or if state equals unlocked. That just makes it a bit easier to manage your code when you're sort of trying to debug any errors later on. So we will initialize the state to be locked, which is one of the 2 values that we've said it is allowed to be up here. And we will also define an unsigned long integer called last unlock time. This is going to be set to the current timestamp every time the safe is unlocked, and we're going to use this and compare it to the automatic relock duration here. So once this number of milliseconds has elapsed since the last time the safe was unlocked, that's what we're going to use as our trigger to re-lock the door again to activate the solenoid and stop the bolts from rotating. I've got a couple of helper functions. I've described them here. So these are functions with a particular sort of purpose to control one particular aspect of the puzzle. This one here, this updates the 8-digit 7-segment display with whatever the currently set input code is. So very simply, it loops over for the entire code length each of the elements in the input code array, and it sets the value of the LCD display at that position based on the value that's in the input code here. You'll see I'm doing code length -1 -i here because we're sort of counting backwards. The way you fill in the LCD display is from right to left rather than left to right. So we're counting backwards from the end, but we're iterating through the input code from left to right. So that's why there's a minus there rather than a plus. This function here, so this one updates the 7-segment 8-digit display, so the code numeric readout. This one updates the 3 LEDs on the front of the safe door with just a different pattern, just to make it look a bit more visually appealing and to give some indication of when the safe has been successfully unlocked or not. And we're going to set different LED chase patterns depending on the state variable here. As I said, that can take 1 or 2 values. It can be locked or it can be unlocked, which are the 2 enumerations we defined at the top of the code. When it's locked, the effect we're going to generate is to just make a red dot sweep left and right, a little bit like the Knight Rider, kind of front of the Knight Rider car effect or something like that. Fade to black by, beats in 16, CHSV. These are all functions that are declared in the fast LED library, which I've included at the top here. This is a really great library. If you're not familiar with it, I really do encourage you to check it out, because it has so many useful functions for doing all kinds of animation effects with LEDs, or just generally setting programmable LEDs to do all sorts of very clever things. So all of these functions are defined there. So the first thing we're going to do is do a gradual fade out of whatever the previous LEDs shown were. So that will make like a nice fading trail basically behind the dot. This beats in 16, so this will be a 16-bit value that based on a certain amount of kind of beats per minute basically. So we're going to do, if it's locked, it's going to be 20 beats per minute or 50 beats per minute. We're going to have this LED sweeping backwards and forwards, and it can go at different speeds essentially. And we can also make it change its color. So depending on whether it's locked or not, we can either set the hue to be 0, which is a red value, or 100, which is a green value. This is the brightness. Sorry, this is the brightness and this is the saturation. So how intense the color is going to be and how bright the LED is going to be. And like I say, these functions, we've also got another function here which I call fill rainbow, and this is the one which is going to fill a gradient across however many LEDs you have. Now you don't really get much of a sense of that when you've only got 3 LEDs in a line, but if you have an entire chain of LEDs, you can get much more dramatic effects. And I'm going to shift the starting value of the gradient forwards by the millis amount. So what that's going to do is it's going to cause the rainbow to kind of cycle forwards through the whole color spectrum for the amount of time. So you can really put anything at all you want here. You could simply have something like, you know, lights on going to lights off when it's unlocked, or just changing from red to green, or anything you want. I've just put these in as demonstrations essentially of some of the things you might want to do. And then we actually call the show function on the LED library. What these functions here do is these set the values in the LED array, which we defined at the top here. So this has got 3 elements in it that give us the RGB value of each LED. And then the fast LED.show function is actually what pushes those values out to the clips on the LEDs. We've got a scramble lock, another helper function here. And this is very simple as well. So again, this just iterates the entire length of the code, all 8 characters. What it does is it's just going to set them a random value between 0 and 9. Nice and simple. And I'm calling this function at the moment. Every time the safe door is opened and closed again, it re-scrambles the lock for next time. So at this point, you're not going to get that visual cue anymore. It doesn't matter if you've got the answer written down on a bit of paper or something else, because it's going to be completely randomized. You're going to have to go by the audio cues to let you know when you've got the solution correct. So you may or may not want to use that. If you were using this in an escape room, you probably not want to ever set a random solution, because that's going to be very hard for you to give any hints as to what the right answer might be. But if you just wanted to set this as an electronic puzzle for your own benefit, or you know, for other people to solve, it might be quite fun just to have a random code each time and just to have that automatically set, and then you can time people to see how quickly they could crack the safe or something like that. So that's an option available to you. And I think this is the final helper function. Yes, this is the final helper function. This enables us to read from the rotary encoder. So the rotary encoder I'm using is a very common cheap type of rotary encoder, which is a quadrature encoder. So it has 2 lines. It has a data line and a clock line. And when the dial is rotated clockwise or anti-clockwise, those 2 lines move up and down, but they're kind of offset by each other. So one will move high, and then shortly after it the other one will move high, then the first one will move low, and then the second will move low behind it. But if you were to rotate the knob in the other direction, the order in which the pins would change high and low would be different. So that's how you can tell whether it's a clockwise or an anti-clockwise rotation, is through the pattern of high and low that these two lines, the clock line and the data line, change on. And only some combination of those changes are valid. The problem is that these encoders can be quite noisy, and also if you're running a code that for whatever reason is slowed down, if you use delay in your code, if you're doing a lot of serial.print statements or trying to control other devices that are slowing your code down, it's possible to miss some of those state changes, some of the highs and lows that these two lines go on. If you don't run your loop fast enough when you're trying to read from the two pins, you can actually miss some of the state changes. And that can have the effect of the rotary encoder reading being jittery or not detected or incorrectly detected, so it thinks a clockwise rotation is anti-clockwise. So the reason I've written this code here, this might look a bit complicated what's going on here, but this is essentially a way of, it's a little bit like debouncing a button, a regular button input, so that you get less noisy values. I'm sort of trying to debounce the rotary encoder input to ensure that when I take a reading from it, the result I get is actually a sensible value that would have been possible given the previous state. So I've got an array here that defines the order of previous state, next state values, and then I keep track of what the current code that we're on is and compare it to the one that I read next time and see whether that's a valid state change, and if it is, whether it is a clockwise or an anti-clockwise change from the previous one. If neither of those are true, I basically return a 0 to show that it was not a valid change, so we'll take another reading. So this is a little bit complicated. I've used this function before in lots of my code, so that was a very brief overview there, but that's essentially what we're doing here, is we're taking a reading from a rotary encoder and also trying to, like I say, get rid of some of the noise to get a nice clean reading. And I find this pretty reliable way of getting a reading, even from a very cheap rotary encoder. It's a good way of getting sensible values from it. So that's the end of all the helper functions, as it were, all the stuff that's to do with specific components. Now we get on to the main meat of the program code. So first of all, we have our setup function. This is the function that runs when power is first supplied and the microcontroller starts running the code. We initialize a serial connection as always, and we dump out the name of the sketch and the date at which it was last compiled, just for debugging purpose. We initialize all of the GPIO pins, and they're either input pull-ups in the case of the encoder, they're outputs for the piezo and the relay. And we also just write a high signal to the relay and then turn it off again. So every time you power up the device, it's going to briefly unlock the safe door just for a second, because I find that's a useful, as part of the reset mechanism. You want to just quickly be able to open the safe door, check that it's got whatever prop inside it that it's meant to contain, or check that it still works. So every time power is supplied, the safe door is briefly going to unlock and then relock again. We also test the piezo by sending a small sound effect there, and then just stopping again, just to make sure that you can hear it in whatever environment you're setting this component up in. We initialize the LED display, so these are all functions that are built into the LED control library I'm using. And then we also initialize the programmable LEDs on the front of the safe door, so we call the add LEDs method. We say the type of LEDs we're using, the pin they're connected to, the color byte ordering in any values we send as well. This is the array of LED values, and we've got 3 elements in that strip. And finally, we get on to the main program loop. So this is just the section of the code that goes round and round again for as long as the program is running. And on every iteration of this loop, what do we do? Well, the first thing we update is the LED animation pattern on the front of the safe. So this is the thing that lights either that red fading LED trail or the rainbow effect or things like that. We call that every frame. Then what we do is we test whether the safe is currently unlocked and needs locking again. So we do that by this if statement here, and it's got two conditions that it's testing. The first is if the state, so if the variable of the controller that's called state is currently in the unlocked state, and also if the difference between the current time, that's millis, and the time at which it was last unlocked is greater than the duration that we set right at the top of the code, the automatic relock duration here. If more time has elapsed than that, then what we want to do is we want to lock the door again. So we write a low value to the relay pin. We scramble the code. As I mentioned, you might not want to do that if you were using this in an actual escape room. You probably want to keep a constant code, but if you want to set this more as a challenge box for yourself, you might want to reset a randomized combination each time, and we'll update the state to locked again. Okay, so that's the next thing we do. Then what we do is we see, well, has there been any input made by the player since last time we checked? So we will call the read rotary function I just described, and we'll store the value in knob change. So this is either going to be -1 for a counterclockwise rotation, or +1 for a clockwise rotation, or 0 if no valid rotation was detected. Now, if it has been rotated since last time, what we need to do is first of all work out whether it has changed direction or not. So if we were rotating clockwise and now we're going anti-clockwise, or the other way around, that's when we advance on to the next digit in the combination. If that would take us to the last digit in the code, then we just wrap around back to the first digit again so that we can't accidentally shoot over the end. And we store the new last direction so that next time we can tell whether it's changed again. The next thing we want to do is to increase the value of the digit in the current position. And also we wrap the value around. So this wrap around up here is if we get to the end of the code. This one is about if the digit that we're currently increasing gets more than 9, we'll reset it back to 0. There is no way using this input system to ever reduce a value, or only ever increasing it and then it wraps around to 0 again. So there's 10 different values. If you overshoot, you just keep on going back round again and it resets. And then we test whether the current digit that has been entered at this position of the code is equal to the correct digit in the solution code at this position. If it is, that's where we're going to play our success sound effect. So I'm calling the tone function, which generates a waveform that is going to be played on our piezo. It is going to be at this frequency for this duration. And you can play around a lot with these values. Basically, the longer the duration is going to be, the more it's going to sound like a beep, essentially. And the higher the value here will make it a higher beep or a lower beep for lower values. If you want to have something more like a click, you can make that value much shorter here. So this is only 5 milliseconds, which means that there's so few iterations of the wave produced that essentially it's not a discernible note of any sort at all. But you can get a high frequency click with a high value, or you can get a low frequency click with a lower value. So experiment with these values, and also depending on the, what aesthetic you want to create with this sound effect, whether you want it to sound more like a sci-fi electronic beep, or whether you want it to sound more like an old-fashioned click, mechanical click, you can sort of play around with those values a bit. But we're going to give two different sound effects. This one is if the digit is correct, and this one if it isn't. And then we'll update the LCD display with whatever the current code value entered by the player is. We will also output that to the serial monitor connection. This doesn't get used anywhere in the game, it's just for debugging purposes. Again, it's very useful to have the Arduino serial monitor open just so you can see the values that are being entered, and if you're trying to investigate any behavior or configure the code, anything like that. And the final thing we need to do is to check whether the code that has now been entered is the correct code. So this is only going to apply if the safe is currently locked at the moment anyway. You can't unlock a safe that's already open. And we'll call the str_enComp function. This is a built-in C function that's going to compare two strings, or it's going to compare the nth number of characters in two strings. So we're going to compare the input code, that's the thing that we've been changing as we enter different values. We're going to compare that to the solution code, which is what we defined at the top here of 1, 2, 3, 4, 5, 6, 7, 8. And we are going to compare 8 digits of those two codes. And if there are no differences between them, that's why we're setting it equal to 0, because that's how the str_enComp function works, is a value of 0 means that these two are the same to this many digits. In that case, well, we've got the solution correct, so we will write a high value to the relay pin. That's going to cause the solenoid to retract, and so that the bars will be able to move across, opening the safe door. We'll set the state to unlocked, and we will update the last unlock time to the current timestamp given to us by millis. And what that means is that 5 seconds in the future, or whatever value you've set the automatic relock duration, this function will be able to kick in again and re-secure the safe. And that's it. So that just about brings me to the end of this video. I hope you found this a useful and informative project, and whether you want to make the same modifications as I've done, or maybe you just want to use one of these small safes in a different way in your escape room, hopefully I've been able to provide you a little bit more information about how you could go about doing that. Now, as always, I'll be putting the ESP32 sketch together with the wiring diagram and any other resources over onto my Patreon account, which I will link to below. And as always, I want to take this opportunity to say thank you so much to all my Patreon supporters who enable me to create these tutorial videos each month. I really, really do appreciate your ongoing support. So thank you all very much. Other than that, if you have any questions or comments or suggestions about this project or any of the other tutorials I've put in this channel, please do write them below and I'll do my best to get back to you. Other than that, I just want to say thank you for watching and I look forward to seeing you next time. Okay, cheers, bye.